Okay, welcome back everybody to the 6th video in our second playlist. This time we're going to be looking at an example of a Kalman filter trying to track constant velocity motion. We're talking about non-accelerated kinematic motion in one dimension. So there are two states, position state and velocity state. System dynamics is still quite simple. The first state is dynamic in that the position is equal to the prior position plus the velocity times the time. And the second state, x2, the velocity state is not changing. It's constant velocity. Now, as far as measurement goes, we have only a position measurement. So the H matrix will actually be a row vector. And now you can see what the matrix math looks like. We've just translated this difference equation into the phi matrix right here. First equation corresponds to the first row in the phi matrix. The second equation corresponds to the second row. It's very clear. Because we only have a position measurement, the H matrix is a 1 and a 0. If we had both a position and velocity measurement, we'd have a 1 and a 1. For our first simulation, we're going to assume that the process noise is 0, but we still have some measurement noise. Later, we'll ramp up the process noise. Okay, even though we're assuming the acceleration is truly 0, if that were not the case in the real world, we could put some process noise into the velocity component and compensate for that, even without having an explicit acceleration model. As I mentioned, we're not going to deal with any process noise in the beginning, and we will add in some process noise. Okay, so here's the covariance extrapolation equation. We have to pre and post multiply by phi and phi transpose. So you see that going on here, and then add in the process noise. When you do the matrix math, you come out with something that looks like this. Okay, we've decluttered the right-hand side by not using the k-1s and the plus and minuses that might be there. So keep that in mind. The Kalman gain computation is left as an exercise for you. All right, so let's take a look at some filter performance first without process noise. And there's no process noise in the truth model either. So what we see here is a position measurement that's bouncing around the true value. It's ramping up to the right because we have constant velocity. And the constant velocity is also reflected in the bottom graph with a straight line going across. So the initial value is just kept at 1 the whole time. Now our estimates on the top graph of position are pretty good because we have the measurements to rely on. However, we have to rely on the state dynamics to propagate our velocity estimates, and as you can see, they're not quite as good. They're bouncing around a little bit more. So as far as the Sawtooth plot is concerned, even though we don't have process noise, it still goes up quite a bit and then comes back down with each measurement. But it gives us some uncertainty just due to the uncertainty in the propagation of the dynamics. All right, so now here's a little bit of process noise, not very much, that's added. We still get pretty much the same kind of profile. There's not enough process noise added to make much difference. Performance of the RMS value and velocity is very similar to what it was before. And here's our sawtooth. Also very similar to what we saw before. Okay, but now we're going to add in larger process noise. And watch what happens. We do get a larger value for the RMS velocity error and also for the position error, but nonetheless we're still tracking with the same measurement noise. We're still tracking the velocity or the position states pretty well. Now we get a completely different pattern with this larger process noise in the sawtooth chart. So for starters, we're ramping up to a much higher level than we had before, about 2.5, and then flattening out there in our steady state. We're not coming back down anymore and just bouncing around. It's still stable, but it's not quite as accurate. And now, in addition to the large process noise, we've added in the large measurement noise. So you can see here that the measurement is bouncing around the truth quite a bit more, and also because there's also process noise in there, the estimate is going to be following a certain amount of measurement and a certain amount of process noise. It's not quite certain. So we've got much worse performance, 1.67 in the RMS position error and 0.3103 for the velocity RMS error. Same pattern on the Sawtooth, but you'll notice the scale is different. We're getting up to about 6.5 before we settle out. Okay, now I want to switch over to our simulation and take a look at the Python script and see what we can do with that. Now you'll notice that, let me go back up to the top here. Couple of things that are different from the previous simulations. One, I've added in a random seed so that we can reproduce the random number generation on each run. That's good for control purposes, so we can make sure we compare apples to apples. Also, I have now exhibiting with NumPy matrix. So here's the phi matrix with the delta t in the top row and a 0, 1 in the bottom row. And of course, our Q matrix is also a matrix. Now this is with that last process noise, small process noise that I put in there. Now a new feature here that I've added in, besides the matrix math, is this thing I call the process noise assumption factor. This has to do with what the ratio is of the amount of process noise that's assumed in the filter model versus how much process noise is assumed to be in the truth. And this can help you do some studies, parametric studies, to see how well your filter is doing, depending on how good or poor your assumptions are. So in this case here, I've assumed that the process noise assumption factor is 0.8. So whatever the variance is, or the standard deviation on the process noise is, the truth will have a slightly smaller amount, but about 80%. So let's see what happens. Let's run this simulation. First we'll move it over and make rooms for our plots. And now we'll run a simulation, see what we get. All right, looking first at the TME plot. You'll notice that in the velocity line down below, we do not have any sort of straight line. It's kind of wiggling around a little bit. It's because of the process noise we've assumed. However, we're still doing pretty well in our position estimate. You'll notice that the black line is hugging the blue line pretty well, even though the measurement noise is bouncing around. So there's some real process noise in the real dynamics, and there's also some in our assumed model. That's a good thing. You always, if there's any uncertainty in your model, you always want to have a little bit more uncertainty in your process noise to compensate for that. Okay, that'll do it for this video. Let's see where we are. So we've looked at the constant velocity model with two states and a single measurement. We've shown how we can change the assumptions regarding the process noise in the truth versus that in the Kalman model. So what's next? Next, we're going to look at the damped harmonic oscillator, which will have dynamic states in both position and velocity. So we'll see you in the next video. Take care.